All right, welcome back. We are now going to talk about complex limits. So all of calculus is based on the idea of looking at local behavior of functions. This is kind of what we're going to be doing in the complex setting, but it's going to be more complicated than in calculus. Because in calculus, you get this idea that limits are always computed by, you check if the limit is doing what it's supposed to be doing from the left, and you check to see what it's doing as you come in from the right. And as long as the behavior along those two directions agrees, then everything is okay. The problem in the context of anything two variables, and again, thinking of complex analysis is really kind of secretly a structured version of two variable function theory. The problem is that if I'm coming into a point in the complex plane, let's see, I can illustrate this really quickly. If I'm coming into a point in the complex plane, so say this point right here, this is A, and I want to know if a function has a limit at that point. One thing you might think to try is, oh, well, I'll just come in from the two different directions. Well, there's lots of directions because we're working with disks and not intervals now. So around this point A, there is some disk. And what I want to say is that as that disk gets smaller into A, then the behavior of the function stays close to itself, right? That the outputs are predictable. As I bring the circle around A in, that the outputs collect up to some point. And there's no real way to do this with directions because there's an infinite number of directions you could approach A from. If you remember from your calculus 4 or multivariable calculus, it's possible to have functions where the limit agrees, say, on every line approaching, the behavior of the function agrees on every line approaching a point even. But as soon as you approach on parabolas, all hell breaks loose. So we can't use the idea of directions or curves of approach here. We really need to define this in terms of epsilons and deltas because we're trying to capture the idea that the behavior of F is sort of completely controlled by how quickly we're approaching A from all possible directions and all possible curves at the same time. And this is why we need this epsilon delta definition. The big idea of the definition is that as you get close on the inputs, so as you get close, as the inputs pull in, so that's what this part does, right? As the inputs get close to some value A, as the z's get closer and closer to A, that is, you're being crushed into A, then the outputs are also controlled. And that's what this means, right? So the basic idea of an epsilon delta approach here is that as the inputs are constrained, the outputs are also constrained in a controlled way. Another way of stating this is, I state that a function has a limit if you tell me an error for how far F can miss that limit by, and I can give you an error bound for the inputs that force F to be within that error in the output. In words, what we mean is a limit exists if the output of a function, if the possible outputs of a function at a point are controlled by how much I vary the inputs. Small variations on the input lead to controllable small variations in the output. Now, this definition is actually identical to the definition of a limit from calculus. This is the power of thinking about complex analysis as an extension of real calculus, is that this is the same thing. Now, the definition of the modulus has changed. We're using modulus instead of absolute value, but because the triangle inequality holds and all the algebra of absolute values works in the same way, we haven't changed anything. So we can just take the idea of calculus, the idea of a limit, and just lift it and put it over into complex analysis. So because the definitions are the same, we should expect that the theorems of real calculus should also hold, and that turns out to be true. If you remember in Calculus 1, one of the first things you do at the beginning of the class when you're studying limits is you define the notion of a limit, and then you show limits behave in the way that you want them to. If you have a product of functions that have limits, then you can calculate a limit by computing the limits of the functions individually and just multiplying them. If you have a function divided by another function, and those two functions have limits that exist, and the bottom one doesn't go to 0, then you calculate the limit by just dividing the limits of the functions. If I have two that are added, I calculate the limit by calculating the limits and then adding them. So likewise, because the definition of the limit didn't change, we get the same theorems in complex analysis. So I'm going to show you a proof of one of these theorems, then I'm going to encourage you to go to the textbook and work through some of the exercises related to establishing these theorems on your own. So if we wanted to prove that this particular definition held, right, this is the product of limit. So we have, this is an example limit theorem. We're going to assume that we have that f has a limit as z goes to a, and we're going to assume that g has a limit as z goes to a. And what we want to show is that the limit of the product of the functions is the product of the limits. It's standard sort of calculus 1 type of thing that we use all the time. And I at least want you to see, for those of you that haven't done a lot of these type of analytic proofs before, how an epsilon delta proof works. Now this proof is optional. I'll tag this. The idea of these proofs is that you don't have to watch them if you don't want to. I encourage you to, if you haven't seen analysis proofs before, because this is a good way, especially if you haven't gone into real analysis, this is a good way of getting a handle on what's happening. If you've already been through reanalysis, then reacquainting yourself with the way analytic proofs work in a complex setting is important. Okay, so let's actually prove this. So this is going to be delicate estimates combined with the triangular inequality. And in fact, basically every analysis proof in some sense typically boils down to figuring out a way to apply the triangular inequality. So we're going to construct a couple of estimates first. We're going to assume the hypotheses of the theorem. That is, we're going to assume that f has a limit at L and g has a limit M. So we'll assume that f of z tends to L and that g of z tends to M as z goes to A. And then we're going to actually, this proof actually works for any A, but we're going to make the simplifying assumption that A is equal to 0, knowing that all we're doing at the end of the day is making the algebra simpler. And the way that we designated these arguments is I'm going to say, without loss of generality, let Z be equal, sorry, let A be equal to 0, just to make the algebra simpler. The argument will still work with the A in it. I encourage you to do that on your own. It's a frequent theme in complex analytic proofs, especially, is to prove them for the value of A is equal to 0, and then just state this theorem, this argument actually works with the A's inside, but the algebra is worse. Okay. So now let's let epsilon greater than 0 be given. And remember what we want to show here. What we want to show is that there exists a delta greater than 0 so that f g minus lm is less than epsilon whenever the input value z is less than delta. If I could show that, I will have proved that this limit exists. So I'm going to carefully construct this delta, and then I'm going to show that it works. So let's let delta f be equal to or be such. Remember, f has a limit at 0, which means that I can, for any epsilon, I can find a delta that guarantees that the output is controlled by the input. So let's choose delta f so that the distance from f of z to L is less than this odd looking quantity epsilon over the modulus of L, epsilon plus 2 times the modulus of ML, whenever the modulus of z is less than delta f. And likewise, we'll let delta g be such that the distance from g of z to M is smaller than epsilon over 2 times the modulus of L when the modulus of z is less than delta g. And then the delta that controls both of the functions simultaneously will just be the minimum of these two, so that both inequalities hold at the same time. So let's let delta be equal to the minimum of delta f and delta g. Then, now we're going to use the triangle inequalities. This is going to be a fancy setup just so that we can invoke the triangle inequality. All right, so we're going to start with this. So fg minus lm I'm going to use what's called an add subtract trick. I'm going to add and subtract a term here, which is going to let me break pieces off using the triangle inequality where I actually have control over what's happening. So this is going to be equal to FG minus LG plus LG minus LM. Now I'm going to hit this with a triangle inequality. So this is less than or equal to FG minus LG plus LG minus LM. Standard sort of thing. Now, this is giving me pieces I can factor. So this is equal to, oh, there's a G contained in the first guy. And then we have F minus L. In the second one, I have a modulus of L times G minus M. And now this is closer to things I have control over. F minus L I know is small because I've set this delta up so it's small. G minus M is small because I've set delta up so that G is as close as I want to M. The problem is this absolute value of G here. I don't know what this is. So the idea is to get that absolute value of G or modulus of G to break that into pieces I have control over. So I'm going to use another add subtract trick. So this is equal to modulus of G minus M plus M times F minus L plus modulus L G minus M. And then using the triangle inequality again on this part, I get that this is less than or equal to modulus of G, minus M plus modulus of M times modulus of F plus L plus modulus of L times the modulus of G minus M. And now basically everything is small here because I have these estimates that I wrote right here and right here. So this estimate and this one. So if I have a pile of positive numbers and I add bigger positive numbers in, I get an inequality. So this is less than or equal to, well, this bit right here, G minus M, that's less than, let's see, epsilon over 2L. So I get an epsilon over 2 modulus L plus a modulus of M. And then I have an F plus L, or sorry, an F minus L. Minus L. And F minus L is smaller than this weird looking epsilon, absolute L, epsilon plus 2 modulus ML. That was using this inequality. Put 2 stars here so I can designate. This used the second inequality right here. And then this is a modulus of L, and then I've got a G minus M, but G minus M is epsilon is less than or equal to epsilon over 2 modulus L. And now stuff just cancels. This is just algebra at this point. So if you walk through the algebra here, this is less than or equal to epsilon. That's not hard to see because what happens is the modulus of L cancels with the modulus of L. In this quantity right here, if you combine this as a fraction, it turns out to be exactly equal to this fraction, but with an extra epsilon floating around in it. And yeah, you get epsilon over 2. It's like magic. So have we proved what we've intended to prove? How do we know we're done with the argument? And the idea is we started with the assumption that delta, that we had an absolute value, or that we had some delta, and we assumed that the modulus of z was less than delta. And what we've proved is that this quantity right here, and we're all done, what we've shown is that this quantity is less than or equal to epsilon when z is smaller than delta, which is precisely how one of these arguments works. This is one of the more complicated of these. So I encourage you to go through it if you didn't totally understand what was happening here. Okay. Like I said, that part is optional should you wish to have it be optional. Right. So the upshot is limits work the way that you think that they should. The limits follow the same rules they do with complex limits or with real limits. So if you know how limits work in real variables, you know how they work in complex variables, as long as everything exists. So one of the first things that we do when we define a limit, the next move in calculus is to build these difference quotients. And so that's the very first thing that we do. We're going to basically just write down the definition of the derivative from real calculus and use the modulus instead, or a complex limit. And we're going to make that be the definition of the complex derivative. So with that said, we make the following definition. So if f is a complex function, then we're going to define the derivative of f at a point defined to be equal to this difference quotient, which should look awfully familiar because that's the difference quotient that you get from calculus. This is the difference quotient from calculus 1. Now, the one difference here is that this limit is computed with complex numbers. So that h is a complex number. And then when we say the limit is h goes to 0, the way you should be thinking about that is that there's a disk centered at A and that the h's come from that disk and are being pulled in. So don't think of it as sequences, the way that most people think about limits when they think about, you're trained to think about real limits in terms of sequences approaching some value. This is a complex number. And so when you do this definition of the derivative and you're doing this sort of complex limits, what you're thinking is there's some point A and the h's are coming from some small ball around A. So there might be h's in here. So to say that limit is h goes to 0 is to say that we have smaller and smaller and smaller disks pulling into the center that are pulling the whole limit with it. Okay. It's easy if you've seen complex variables before to get the idea that complex functions are like, having a complex derivative is the nicest thing in the world. You have to be a little bit careful because just like functions of real variables can be differentiable at only a point, the same thing can happen in complex variables. So this function, f of z is equal to z squared, is a function that is differentiable only at 0. And so involving modulus in a function can actually, the way that you think about like why that might be happening is maybe you get some sort of weird cuspy type behavior. I'll be walking through how to visualize some of this stuff later. But the idea is that it's possible for this difference quotient to only be defined as a single number. It's worth taking time to look at this example and try to figure out why. So as an exercise, try to figure out what's going on. Try to figure this out. Check this computation. Okay. Now here is the single most important definition in complex analysis because it leads to everything else. That is the idea of holomorphy, which means I want to exclude the possibility of functions that can be differentiable only at a single point. So I'm going to introduce a much stronger condition, which is eliminating places where functions just have single point good behavior and forcing them to have behavior on some small set, some small open set, which is a very, very strong thing to ask, it turns out. So we call a function holomorphic at a point if f is complex differentiable not just at a single point, but at every point in some disk centered at z0. That is a major ask for a function because it means locally at some small open set, that graph of that function is nice, well approximated by tangent planes, not just at a single point, but in all the points around some single point. It might not seem like that's a very big ask, but that move in itself is enough to basically create the difference between real variables and complex variables. So holomorphy is a big deal. So the idea here that what I want you to think about being holomorphic at a point is not just a condition where the limit exists at one point. It exists in some open neighborhood of that point. So this sort of disk right here, when we say that a function is holomorphic, we mean that the derivative exists everywhere inside a little disk like that. So holomorphic means differentiable on a small disk. And then we use the typical sort of language after that, right? So a function is holomorphic at a point if there's some small disk around that point where the function is differentiable everywhere near there. If a function is holomorphic everywhere in its domain, we call the function just holomorphic. And if a function is holomorphic everywhere, for every complex number of a complex derivative exists, we call that sort of function entire. And we're going to give examples of these once we get the extension theorem. And you can already think about the functions of real variables that are differentiable everywhere. So e to the x, for example, is a function that has a derivative everywhere and is in fact infinitely differentiable everywhere. And we'd like our function theory in complex variables to recover some of those ideas from real variables. So let's actually check and see how you would prove that a function is differentiable. So let's look at the function f of z is equal to z squared. So the claim is that this function is differentiable for all z and c. So let's just compute the limit. The limit, as h goes to 0, we're going to compute this precisely the same way that we would compute it for calculus. So we're going to write down a difference quotient. F of z plus h minus f of z divided by h. Remember, as long as the complex limits exist, they act just like real limits. So hopefully we get to the point at the end of this where we can just plug 0 in for h. Right, so let's compute it. Well, this is equal to the limit as h goes to 0 of z plus h squared minus z squared over h, which is equal to z squared plus 2zh plus h squared minus z squared over h. And of course, that's still in the limit. And this is equal to the z squareds cancel, and we get the limit as h goes to 0 of 2zh plus h squared over h, which is the limit as h goes to 0 of 2z plus h. And that has a well-defined limit. I can plug in, it's a polynomial, and I get 2z. So if all is right in the world, then we should be able to create complex functions by taking well-behaved real functions and just putting z's in place, and maybe the same rules will hold. And that's what we've just done here. We've proved that if f of z is equal to z squared, then f prime of z is equal to 2z. And the hope is that the same differentiation rules exist in complex variables as exist in real variables. That would be another illustration of the theme that complex analysis is an extension of real calculus. One thing to show here that I've not left room for is you can prove that there are functions that are differentiable for no values of z. So the function z bar, f of z is equal to z bar, is differentiable for no value of z. The reason that it's differentiable for no value of z is because you can approach 0, say, you can approach z from multiple directions, and you're going to find that you get different values. So I can do that real quick in this room up here. So let's compute this difference quotient for this function f of z is equal to z bar. And this gives us idea that bars are bad in these functions, right? Like in the involvement of a complex conjugate is going to be a barrier to a function being well behaved. So we'll compute the limit as h goes to 0 of z plus h bar minus z bar over h, which gets us the quantity, the limit as h goes to 0 of h bar over h. Now, if you remember two-variable calculus, there's a method for proving that limits don't exist that involve approaching a value from two different directions. And so what I'm going to do is I'm going to assume that h is equal to x plus iy. It's a complex number, so it has the form x plus iy. And I'm going to let h go to 0 along two different paths. So the first path that we'll consider is the path where let's look at the path where we're coming in on the real axis. So that is y is equal to 0. If you come in on the real axis, so that h is just equal to x, then you get the limit as x goes to 0 of h bar, that's just x bar over x. Well, those are real numbers now. X bar over x is just x over x, which is 1. So this limit is 1. What happens if you come into the same value along the imaginary axis? Along the imaginary axis, now we're looking at points of the form iy. So on this axis, h is equal to iy. That is, there's no real part, there's just an imaginary part. In that case, the limit as y goes to 0 of iy bar over iy is equal to, well, minus iy over iy, which is minus 1. So I've got two different limits coming into 0, or coming into the point z on two different paths. And that means this limit can't possibly exist. So this limit doesn't exist because we come into different values along different paths. Different limits on different paths means no limit. So it's not sufficient to prove that something has a limit to come in from different paths and show that the paths are the same, but it's definitely sufficient to prove something doesn't have a limit to find two paths where the limit, the behavior of the function disagrees. Okay, so z squared is good, z bar is bad. Bars are getting in the way of differentiability. And that's like going to be a running theme, is that the nice functions of calculus turn out to be the nice functions of complex analysis. And there's gnarlier functions that show up in complex analysis that aren't going to follow the good behavior that we want. Okay, so the last thing I want to do in this section is to give you an idea of how a more complicated sort of argument works. This is going to be a proof of an example derivative theorem. Again, this is not required, but you should at least see that these differentiation theorems that hold from your undergraduate calculus also hold in complex variables. So as an example of these theorems, Johnston presents in theorem 1.1.3, we're going to walk through the optional proof of proving the power rule for differentiation. And I'm going to show you that it's the same proof that holds in real variables. Okay, so let's just start by writing down the difference quotient. So the limit as h goes to 0 of z plus h to the n minus z to the n over h. And this is actually going to require that you know the binomial expansion. So this z plus h to the n squared, the easiest way to write that down, if you know your binomial expansion, put it over here, is that if you have x plus y to the n, this is equal to the sum k goes from 0 to n of n choose k, x to the k, y to the n minus k. This is the form of the binomial expansion. This is attached to the idea of Pascal's triangle, for example. Right. So what happens? Another way of you can actually write this as the sum if you really want to. This is equal to the limit as h goes to 0 of z to the n plus nz to the n minus 1 h plus n choose 2 z to the n minus 2 h squared all the way out to n h to the n, and then we subtract the z to the n and we divide by h. So this is where I've used the binomial expansion. So you should notice what's going to happen here. This term and this term are going to cancel. And then there's going to be a single term in the top with just one h in it, which is this term right here. And every other term will have an h, which means when we divide, every term except the n z to the n minus 1 term is going to disappear once I put in h is equal to 0. So this is equal to n z to the n minus 1, limit in there, limit as h goes to 0 of n z to the n minus 1 h plus n choose 2 z to the n minus 2 h squared out to h squared h to the n all divided by h, which is the limit as h goes to 0 of n z to the n minus 1 plus n choose 2 z to the n minus 2 h out to h to the n minus 1. When you take that limit, all of these terms have an h in them, so they all cancel. And what you're left with is n z to the n minus 1. And so as hoped for, the same arguments that held for real variables hold in complex analysis here at the bottom, right? So the idea of complex derivatives follows direct, and the rules for the arithmetic of complex derivatives follows directly from rules that we already know from calculus. So again, to reiterate the theme here, the basic bones of complex analysis are built from the bones of real calculus. And the assumption that we've made that's the really different one is the idea that we're going to be focusing on functions that are differentiable, not just at a point, but differentiable around points in some little open set. And from that assumption or that definition, all of the rest of the structure of complex analysis is going to follow. So next time what we'll talk about is power series and the extension theorem. So one of the most important facts in complex analysis is the existence of a derivative is actually equivalent. I should be careful here. Being holomorphic at a point turns out to be equivalent to having a power series. And the point of the next lecture is to take what we've done with the derivative and show that our notion of derivative combined with our definition of holomorphic turns out to be enough to guarantee that a function actually has a convergent power series. And that is the sort of why complex analysis is so nice. All right, so I'll see you next time.